the hydration of alkynes. And this is going to be analogous to some of the reactions we saw with alkenes. And back in the day, we saw 3 different reactions for alkenes. Well, we're only going to have 2 different hydrations for alkynes, and they'll have some similarities, but some key differences to those similar reactions. This lesson is part of my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one or any of my future playlists, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new lesson. All right, so let's go back and review those alkene reactions. And we had acid-catalyzed hydration. And acid-catalyzed hydration, it was either written as dilute H2SO4 or like H2SO4 in water. And in this case, or H3O plus technically. And in this case, it has an H and OH Markovnikov. It goes through a carbocation intermediate, which is subject to rearrangements in some cases, not the case. H on the less substitute side, OH on the more substitute side, adding water, hence hydration. We also had oxymercuration-demercuration, which did not go through a carbocation, was not subject to rearrangements, but still went Markovnikov, adding an H to the less substitute side, OH to the more substitute side. And then finally, we had Hydroboration-Oxidation, which added H and OH anti-Markovnikov across. So OH on the less substitute side, the H ended up on the more substitute side. And what we're going to find out is we don't have 3 options with alkynes, we just have 2. And the first option is going to kind of be like a combination of the 2 different ways we do Markovnikov addition of water with an alkene. And then the third way is going to be hydroboration-oxidation, or the second way I should say with alkynes is going to be analogous to our third reaction for alkenes, but it's going to be hydroboration-oxidation. So if we look at acid-catalyzed hydration here, it turns out with a terminal alkyne here, like we're going to use here, so we can see the difference between Markovnikov and anti-Markovnikov, it's not sufficient just to use dilute H2SO4. You need a mercury 2 plus catalyst, either written as just simply Ht2 plus or most commonly as HgSO4 as I've written it here. Some people also want to show that H2SO4 here is dilute, and either they write dilute like we did over here with alkenes, or they write include water as one of the reagents as well. Totally a little bit on up to your professor on how they write it. So, but you'll see it commonly with or without the water, but yes, it's a aqueous solution here. All right. So it turns out with hydration reactions, we don't have the option of adding 1 equivalent or 2 like we had for like hydrohalogenation, halogenation. Turns out we're only ever going to get a chance to add 1 equivalent because as soon as we add that 1 equivalent, we're going to have a transformation of that intermediate into our final product before we ever get a chance to add a second equivalent. So if we take a look at the result here of adding 1 equivalent of H and OH as it occurs here, so we got 1, 2, 3, 4 carbons, so 1, 2, 3, 4 carbons, and we're still going to have an alkene after 1 equivalent is added, and the OH on the more substituted side, we add an H to the less substituted side, so and we have an interesting situation going on here. So this carbon right here is part of 2 functional groups. It's part of an alkene and it's part of an alcohol, and in which case we actually can't treat them as separate functional groups. You'll see there's some resonance going on, some delocalization with the lone pairs and the alkene pi bond, and as a result, this is not just an alkene and it's not just an alcohol. They're part of a common functional group now that we call an enol. It's both an alkene and an alcohol from the same carbon. And due to resonance or delocalization, it has some different properties than just a regular alkene or just a regular alcohol. And it turns out these enols undergo what's called tautomerization. And so it turns out we're going to keep the carbon backbone exactly the same. So 1, 2, 3, 4 carbons. So, but we're going to end up with a carbon-oxygen double bond instead. And so right where we had the carbon-oxygen single bond and an OH, it's now just a carbon-oxygen double bond and the H is gone. Well, that H isn't really gone, it's just been moved around, but it's not obvious where it's been moved around. But if you look, this carbon in the enol intermediate right here, so has got 2 hydrogens, and now in the product, it's a methyl group and it's got 3. So this hydrogen that was on the oxygen gets moved over to this carbon. So this isn't simply a matter of resonance, because in resonance, you're not allowed to move atoms around, just electrons. So we call this process tautomerization. Big, long, funky word. So, and this is the keto form over here. It's a ketone in this case, and this is called Keto-Enol Tautomerization. And most of the time, having the pi electrons between the carbon and the more electronegative oxygen is more stable than having it between two carbons. And so in this equilibrium that's established, it heavily favors the keto form. And so as soon as you form this enol, after the addition of one equivalent of water, you don't get a chance to add another equivalent across there because it tautomerizes, and the ketone is your actual product. We just view this enol as an intermediate. So if you're asked to predict the products, you shouldn't be drawing the enol here. That's just, it turns out, now an intermediate along the way. The ketone over here is your final product. And because we no longer have a carbon-carbon double bond, but a carbon-oxygen double bond instead, we can't do an addition reaction across an alkene because we don't have an alkene, and that's why we no longer get a chance to add a second equivalent for these hydration reactions. Okay, so this is, notice, a combination, if you will, of these reactions right here. In a sense, it involves dilute H2SO4, part of the reagents, and it also involves mercury, which is part of the oxymercuration-demercuration, but it's kind of like combined into the same one. Now we'll find out in a little bit here that for an internal alkyne, you don't need the mercury. It's only for a terminal alkyne that you actually have to have the mercury as a catalyst to get this reaction, to get any kind of good yield of your ketone product. All right, we also have hydroboration-oxidation, and once again, we're going to see some differences. It is going to be analogous to what we did over here, but oftentimes we use a little bit different reagent. Instead of using BH3, borane, complex with THF, we often replace that with what's known as a bulky borane. So in this case, SiA2BH stands for disiamylborane. I'll put its structure up on your screen. But we essentially take borane and we replace two of the bonds to boron with bulky carbon chains. So if you look at your handout, if you got the handout, or I'll put the picture up on the screen, you'll see that disiamylborane or dicyclohexylborane or 9-BBN, things of this sort, those are your classic bulky boranes. And sometimes we just write it generically like this, R2BH, and it works better. And the idea is that when this reaction happens, boron loses a hydrogen. Well, if you start off with a boron that only has one hydrogen instead of three, well, then the reaction only ever has a chance of occurring once, and we get a little better yield with our alkyne. And the alkyne, again, having two pi bonds, might actually react twice if we use the other reagent. Well, here's the deal. You're going to get a better yield this way. However, if you just still used borane, BH3THF, in step one with an alkyne, you're still going to get the same major products, just maybe in the lab not quite as good a yield, but on paper, you should still predict the same products. Most of you guys are going to see this with a bulky borane included as your reagents, but some of you guys might see this as BH3THF instead. All right, so let's see how this plays out. In this case, once again, we'll add one equivalent of water effectively across the alkene, net result after one equivalent's been added. And in this case, the OH will end up on the less substituted side, since it's going anti-Markovnikov, and whether it's E or Z doesn't really matter. So both are potentially options here and stuff, but it doesn't really matter. Don't care, because this is once again just an intermediate. This is once again an enol. That carbon right there is part of an alkene and an alcohol, and once again it's going to tautomerize. So your backbone, carbon, 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 carbon to oxygen, all stays the same once again. Let's give myself a little more room. So there's your backbone, all the way to the oxygen. So 4 carbons in a row and then to the oxygen. And once again, you're going to end up with a carbon-oxygen double bond instead of the carbon-carbon double bond. And that H is going to get moved over to this carbon, which right now is 1H, but in the product has 2. And you'll see that this is actually not a ketone, it's an aldehyde. For an aldehyde, that's the one time we expect you to draw a hydrogen bonded to a carbon. So we're going to draw that in. It was there the whole time, though. That H was there all along. And so even though this is technically an aldehyde, we still call this Keto-Enol Tautomerization. Cool, and once again, this equilibrium that forms between the keto form, which is an aldehyde, and the enol still heavily favors the aldehyde in this case as well. Again, having those pi electrons between the more electronegative oxygen with carbon, more stable than between 2 carbons. We'll find out a couple exceptions. There are cases where the enol ends up more stable than a keto. Probably not, you're just not going to see it in this chapter. You might see it later on, and usually it involves some sort of intramolecular hydrogen bonding with the OH and things of this sort, which is not possible here. So, but in more complicated examples that we might see in second semester, you might see that. But for now, just know that you're supposed to predict either a ketone when it goes Markovnikov with the terminal alkyne, or an aldehyde when it goes anti-Markovnikov with the terminal alkyne, are your major products. All right, one last thing I want to talk about in terms of an internal alkyne now. So if you start this reaction with an internal alkyne, either one of these, doesn't matter. And I'm going to pick one that's not symmetrical so we can see the difference here. So with an internal alkyne, there's no such thing as Markovnikov and anti-Markovnikov since both sides of the alkyne are equally substituted. And so as a result, whether you use this set of reagents for Markovnikov addition or this set of reagents, which is normally anti-Markovnikov addition, you won't notice a difference here. And once again, if you go the route of acid-catalyzed hydration, you don't actually need the mercury. You can just add dilute H2SO4 and that would be sufficient. But what you're going to find here, regardless of which of these reactions you do, you can get an enol here, or you can get the enol here. You can add the H or OH either direction. Since each side of the alkyne is equally substituted, then you can do it either way. And so with two different enols, once those tautomerize, you get two different ketones in this case. And cool, so we're going to get two products. And that's also why I mentioned using an asymmetric internal alkyne. Had this thing been symmetrical, so in that case, take off that carbon right there for a second. I'll add it back in a sec. But whether you end up with the ketone on this carbon or the ketone on this carbon, which is kind of the net result here of these reactions, well, whether you did it here or here, it would be two butanone either way. So second in from the left or second in from the right, it's the same diff. And that's why I chose to use an asymmetrical one. That way we'd see that there are two different ketone products in this case when for a typical asymmetrical internal alkyne, Markovnikov and anti-Markovnikov don't seem to mean anything. So now that we've taken a look at the net reaction here for our two different hydration reactions, we saw that with acid-catalyzed hydration, we're going to result in a ketone. With hydroboration-oxidation, we're going to result in an aldehyde, at least when we start with a terminal alkyne. So what I want to look at, though, is that last step in the mechanism, so where Keto-Enol Tautomerization takes place. And so we don't know all the mechanisms for all the different alkyne reactions, and so we're a little bit limited on some of the ones we can ask you about on an exam. Well, the Keto-Enol Tautomerization mechanisms, because there's two of them, is the most common example of mechanisms I've seen show up on the alkyne test. So definitely want to spend some time learning both of these mechanisms. So it turns out one is acid-catalyzed, and it happens when you do acid-catalyzed hydration. It happens under acidic conditions. There's H3O plus in the solution, and so that'll be your acid-catalyzed mechanism. And then with hydroboration-oxidation, the second step happens in sodium hydroxide, and so the Keto-Enol Tautomerization takes place under basic conditions. It'll be the base-catalyzed mechanism. And it turns out that your net result here is just two steps in both cases. There's a protonation step and a deprotonation step. If you look at the difference between your enol and then the ketone in this case, so it is the movement of H plus from one location to another net result. So we need to lose the H plus off the oxygen to form the ketone. So what's not so obvious though is that we need to add one to this carbon right here. This carbon right here has two hydrogens right now. It ends up as a methyl group with three hydrogens. And so the question is like, when I take an H plus off of something, I'm deprotonating it. When I'm adding an H plus to something, I'm protonating it. And the question is really just what's the order of the steps? Because if you're under acidic conditions, then you're going to protonate first. That's what acids do. But if you're under basic conditions, you're going to deprotonate first because that's what bases do. And that's kind of the idea here. So let's take a look at this. So in this first step here, we need to protonate that carbon. That's our first thing. So before we deprotonate the oxygen in the second step. So we're going to protonate this carbon. We're going to use these pi electrons to come get a H plus from H3O plus. And rather than showing resonance here, so this would add an H to this carbon and leave a carbocation here. Most of the time, instead of showing resonance, we just show these electrons dropping down from the oxygen simultaneously. So sometimes on occasion, you'll see both resonance structures, John, but most of the time not the case. So we get this lovely intermediate. This carbon now has three hydrogens. It just picked up its third one in that step. So, and now we have a double bond to the oxygen, and we can see how we're going to get to our ketone at the end. All we've got to do is deprotonate right there. And in addition to forming this lovely species, when you deprotonate water, you deprotonate hydronium, you form a water molecule. So we've got a new water molecule in here as well, and we'll use him to deprotonate. And therefore, in addition to now forming our ketone product, we're also going to form some H3O plus. And so that's our true catalyst. We used up an H3O plus ion in the step 1, but we regenerate it in step 2. It's not consumed in reaction, just like a catalyst should not be. All right, your second mechanism is usually just a teeny bit more challenging because we are going to show some resonance in this one. And in this case, under basic conditions, you're going to deprotonate first. We've got hydroxide in the solution. And so in this case, to get from our enol to our aldehyde, in this case, we're going to deprotonate the oxygen first and then protonate this carbon right here, which is going to end up with two hydrogens in the end. So we're going to deprotonate first. And so we'll use our hydroxide base to deprotonate. All right, that's going to take us, oop, no double bond there yet, jumping the gun. All right, to this lovely species right here, plus we formed a water molecule, and I'm going to draw that water molecule in because we're going to use him in a minute. In fact, I'll put him up here because that'll be more relevant. All right, so in this case, we formed this lovely structure right here, and in some cases, some textbooks, some professors, they'll show it and not show any resonance here. So, but we're gonna show the resonance here. I think it's more commonly shown that way. And so we'll see that we can push these electrons here and show that we can have a partial negative charge on that carbon and via resonance delocalization as well. All right, so there's our two resonance structures. And so the first one is definitely the major. Having the negative charge on the more electronegative oxygen is more stable than having the negative charge on the carbon. It is shared between both. So, but we're going to use the major resonance contributor in the mechanism. That's proper. So we need to protonate this carbon now. So we deprotonated. Now we need to protonate the carbon to get to our final structure. And we'll use the water molecule we just created, add a proton there, and just like we did above, we're going to push these electrons down to form that carbon-oxygen double bond at exactly the same time. So, and that's our mechanism. We're actually done there. Now, in addition to forming our product, we're also going to form some hydroxide. And once again, like a true catalyst, the hydroxide that got consumed in step one is regenerated before it's over, so that way our catalyst is not consumed in the reaction. Cool, one other thing to note, this hydrogen right here, so we normally don't draw hydrogens bonded to carbon except for an aldehyde. And so I drew this hydrogen in here, but it's been there the whole time. That's not the new hydrogen. The new hydrogen got added to this carbon right here. So it's on this carbon, but that hydrogen's been there the whole time. It's just not drawn in because we only draw it in for aldehydes, but there's still a hydrogen right there, just not drawn in. Just wanted to point that out, make sure you saw it. Cool, that's your Keto-Enol Tautomerization. Again, know your acid-catalyzed mechanism, protonate, then deprotonate. Know your base-catalyzed mechanism, deprotonate, and then protonate. Now, if you have found this lesson helpful, would you consider giving me a like? And if you know anybody who'd benefit from this lesson as well, would you consider sharing it with them? If you are looking for more, if you want study guides and practice quizzes on alkynes, if you're looking for final exam help, I've got some final exam rapid reviews. Check them out in my premium course on chadsprep.com.